Hello there and welcome back to this video series on control systems. Over the past few videos, we have seen how the design of compensator in frequency domain goes on. We have also seen what are the frequency characteristics of a lead compensator. In specific, we have seen that it is a high pass filter. It doesn't disturb things in low frequency region. And we have also seen what is the design procedure for lead compensator in a nutshell. We'll see more details in this present video. It goes without saying that if you are very thorough with the body plots, how to draw body plot, and also what is the design philosophy of frequency domain, and also characteristics of the lead compensator, this video will be very clear. After watching this video, a student will be able to design a lead compensator. A bit of practice may be needed, solving a few problems, going through the numerical calculations would deepen the understanding, but this we state as the outcome. As an example, we'll consider a plant with the transfer function given over here. It's a type 1 system. We need to design a compensator and design a compensator using body plot in frequency domain to meet the following specifications. Overshoot to be less than 15%. Settling time should be less than 5 seconds, and the velocity error constant should be around 40 second inverse. Okay. Carefully note that we are expected to undertake the design process in frequency domain, but the specifications are in time domain. So before we actually go and design a compensator in frequency domain, we need to convert this time domain specifications into frequency domain. We'll do that in a little while, but what we'll try to see is if the system is left as it is without any compensator and just use unity negative feedback, will these requirements be met? That is what we need to see before we actually design a compensator. That is, we need to see if a design is really needed. To see if the specifications are already met or not, we'll try to write the closed loop transfer function g over 1 plus g, which comes out like this, from which we see that omega n square is 4, 2 zeta omega n is 1. So because omega n square is 4, omega n is 2 radians per second, and this zeta is 0.25. Knowing the damping ratio is 0.25, you can compute peak overshoot. Peak overshoot, percentage peak overshoot is 44.13, and you can compute what is the settling time. Settling time happens to be 4 over zeta omega n, which is 8 seconds. And we know velocity error constant is limit s tends to 0 s ds, which is 4. So we see that we required a peak overshoot of less than 15%, settling time less than 5 seconds, and kV to be 40. These things obviously are not met. We have a overshoot 44.43%, which is greater than 15. Settling time requirement is not met, and kV requirement is also not met. Since none of the requirements are met, we need to design a compensator, because if we do not use a compensator and consider closed loop system with unity negative feedback, all the requirements, none of the requirements are met. So, design and frequency domain of a compensator is necessary. Since it is necessary, we'll try to convert the time domain specifications into frequency domain specification. That is, we'll try to compute what is gain, crossover frequency, and phase margin. This we do that in the next slide. We are given what is the peak overshoot requirement. So we'll try to write that down. Peak overshoot is 15%, which is so and so, and hence you can compute what is the damping ratio. This percentage peak overshoot is a function of the damping ratio, so you can compute the damping ratio as given here, 0.517. Given the damping ratio and the natural frequency of 2 radians per second, you can compute gain crossover frequency as given here, 1.19 radians per second. And also the phase margin required is 53.17. That is, the requirements are converted into two frequency domain parameters. That is, we require gain crossover frequency to be somewhere 1.19 radians per second, and we require that the phase margin is 53.17. We note that gamma required is 53.17 and this frequency is 1.19. Since none of the criterions are met, we'll try a proportional controller. That is, this GC block which comes over here, we'll take it to be K1, just a constant, a proportional controller. With that, we see that this velocity error constant limit s tends to 0, K1 multiplied by GS is 4K1, and we want that to be 40. So with K1 is equal to 10, the requirement of Kv is equal to 40 is satisfied. And during the course of solving this problem, we'll call this K1 times GS, K1 multiplied by GS, as the gain compensated system. If you put a loop around it, we call it gain compensated closed loop system. Till now, what we have ensured is that this gain compensated system shown in figure A in the previous slide satisfied the velocity error constant requirement. That is, if you substitute K1 is equal to 10, the velocity error constant is 40. But still, we need to see if the gain crossover frequency and the phase margin requirements are met. To do that, we need to draw a Boolean plot of this gain compensated system, which is shown in the next slide. We have drawn it using a computer package Octave, and from that we note that the phase margin is 9.04 and this gain crossover frequency is 6.28 radians per second. Let us quickly go to the next slide and see the Boolean plot. Okay, in the Boolean plot for this transfer function, this is gain compensated system. G1 is 40 by S into S plus 1, 4K1 is 40, and we see that if you project this gain crossover point down and see the gap between minus 180 and that, we see 9.04. So this phase margin specification is not met at all. What we want and what we got here didn't match at all. So we need to try to design a compensator. So if we do not use any controller, the velocity error requirement is not satisfied. Of course, neither do others. That is the settling time and other requirements. None of them are met except kV. Okay, but if we use a proportional controller, kV requirement is met, but phase margin requirement horribly failed. It fell short. This points out that we need a compensator that does not disturb low frequency portion of the plot but reshapes the plot at higher frequencies. Okay, so we need adjustment at higher frequencies without disturbing lower frequency content, and lead compensator offers such facility because this lead compensator is a high pass filter. So we'll see what we are going to do in this slide. This is the gain compensated system, and you have the body magnitude plot here, phase plot here, showing 9.04 degrees as the phase margin. So we want to use a compensator of this form. We know that if we use this lead compensator with value of alpha less than 1, you see that the compensator has a peak here. So it offers additional phase. And what is that additional phase? Additional phase is gamma required minus gamma existing. Gamma existing is 9.04, gamma required is 53.17, so 44.13 degrees of phase if the this compensator, if it adds this much of additional phase, our phase margin requirement 53.172 will be met. Since we have phi m is this angle which we computed just now, the alpha of the compensator is found using this formula to be 1.179. And also, since we have omega m is 6.28, this t term, time constant term, you can evaluate it to be 0.3764. With this information, we write the compensator to be something like this: 1 plus j omega t by 1 plus j omega alpha t. With k1 known and g1 of j omega is also known, the compensated open loop system is k1 g j omega, which comes out to be something like this. Next, we plot the body plot for this transfer function and see if the requirements are met. And this we show in the next graph. Next slide. We saw that the system is stable. Phase margin is 43.4 degrees. Fine. But still, we designed for 53.17 phase margin and we got only 43.4. What went wrong and what are the few things that we missed? We'll try to see that in the next slide. We'll try to investigate that. This slide shows the details and the line of direction that we started. We had this K1G omega 1 for which the gain margin was 9.04. We wanted to add 44.13 because we want to get 53.172. That is the required phase margin. Okay, so this is the lead angle given by the lead compensator. Okay, but we didn't get this 53.172. We got something less. What happened? We will see. Okay? When you use a lead compensator, we assumed it adds only the phase lead and nothing happens to the magnitude. No, it also contributes a magnitude. This contribution of the magnitude We already know 20 log to the base 10 1 over square root of alpha. We derived that. That comes out to be 9.78. That is, there is a change in the magnitude curve, and the magnitude curve, it comes out something like this, because the phase lead compensator also adds magnitude. With that, what happened? We wanted this to be the gain crossover frequency, but the frequency moved here. So that gives us an idea. That gives us an idea that we need to make an adjustment. We should not have the phase lead provided here at 6.28, but we need to have the phase lead provided here. If you provide here at 11.2, this is occurring at 11.2. Okay, at 11 we choose this 11.2 because you see this additional x. If you want to cancel with a minus x, this is the point where you get minus 9.18. So that frequency omega m at which the magnitude is minus 9.18, the frequency we took as 11.2. Okay, if we choose this as the frequency, we have a new design, and we want to be a bit more careful this time. And instead of saying that phi m is 44.13, we add 10 more degrees just to be safe. If we add more phase, even if it falls a little short, we will still meet the requirement. So we added 10 more degrees and found this phi m. Usually 5 to 12 degrees is what is generally added in the design as a thumb rule. But we thought, okay, 10 degrees is fine. We added 10 degrees to it. So gamma requirement minus gamma plus 10 degrees. With this, alpha comes out to be 0.1048. And because we have omega m, we know T is computed here. And with this, the compensator sinusoidal transfer function is given as. So with K1 known and D1 known, the compensated open loop system is, this is the gain compensated, this is the compensator transfer function. So we say this is the open loop, and body plot of this whole K1 G1 is drawn in the next slide. And we got the phase margin, required phase margin 59.3, which is greater than 53.17. We are happy here. Gain crossover frequency, we wanted at least this much, and we got 11 radians per second. So all our things are met. We are happy. The design process ends over here. So though we say it ended here, in actual practice, in your examination you say the process ends here, but in actual practice you will draw the step response of the closed loop system and see that things are fine. However, such approach I am leaving aside now. And here is the body plot of the new compensator included open loop transfer function. We saw that everything is fine. We got what we wanted. Thus, in summary, we see that a lead compensator provides extra phase margin at desired gain crossover frequency. A little more adjustment may be needed to ensure that the additional gain crossed by the lead compensator is also accounted for. Thus, the design process may involve 2 or 3 iterations. You made a little tweak and then see whether the requirements are met. If the requirements are met, fine, we are happy, we'll stop. Otherwise, make another tweak and so on. So at each iteration, you need to draw body plot. So the sooner you can draw body plot, the quicker will be the design process. I think that's all we have for now. Have a great day.